So today we're going to talk a little bit about asynchronous Python. I said earlier, my name is Emmanuel Apau, senior DevOps engineer at Mechanica.io. Here's my LinkedIn and my social in case you want to follow along. The topics we're going to be talking about today is one, the synchronous programming model and asynchronous programming model, WSGI versus ASGI, the concept of monkey patching, async IO, the event loop, and then of course the async await syntax, and then walk through some coding examples. I like to always start with a foundation and things that we already know. So for example, synchronous programming model, because that's been around the longest, and hopefully as we build this foundation, we can then move on to talk about the more asynchronous programming methods, which is what brought us all here today. So without further ado, and before I bore everyone with the boring stuff, synchronous programming model. This means, events can be processed one at a time. When an event is initiated that performs a task, the application is blocked from executing subsequent events until the task is complete and returns a result. So just a real quick demo of what that looks like. For example, let's say you had an application that needs to read a file from the file system. It goes and gets contents for that file, is unable to process any subsequent events during that time, is waiting to collect the contents, prints it out, and then a second request then initiates. That's a very request response type of model. Then the asynchronous programming model would mean that events can be processed concurrently. So as an event initiates and performs a task, the application is free to continue initiating other events while waiting for the response of the original task. So once the task completes and alerts the application with the result that it has ended. So if we go back to our previous example, it would be the app is now sending out a request to read a file. While it's waiting to get the contents of that file, is able to now pick up a second request to read maybe a smaller file, handle that processing in the background, get the response for that second request while still waiting for the original, and then of course printing out the contents of the original request. So that's just a very simple example of explaining the differences between synchronous and asynchronous programming. So let's dive right into what is a WSGI. So you probably heard the term WSGI. It's a web server gateway interface. And these are for applications that are single synchronous callables, that take a request and return a response. So the simple client server programming model that we've all become very familiar with. And a callable, just in case you're not familiar with that definition, is anything that can be called. So for example, like time.sleep, it's a function that you're able to call and so on. But keep in mind that the WSGI is just a specification. So Python, the organization, went and said, hey, when it comes to handling requests and responses, here's a specification for how we would like the server to act. And then other groups have gone and built frameworks to support that WSGI specification. And the most popular one, I think, is Flask, which handles WSGI responses. So a simple Flask server would look something like so, where you're defining an application. You have a request definition as a parameter, and then you have another object that helps create the response. So the start function over here would be a callable, which then creates a response and with a status code and a header, and then you return the response body. And I just want to pause for a second as we're getting this foundational stuff out the way in case anybody has any questions. Cool. So then, yeah, let's dive into a little bit of code real quick, just to kind of show you what that would look like. So you have a basic Flask application. You would import Flask. You have your basic route on the index, and then it would just print a response and return a hello world. Now I'm going to execute this, and then just make a call to the server, and gives us what we expect. We return a 200 with the response body, hello world. Now, what we're going to be seeing in future examples is a concept of an app being blocked. And that's where the application, the Python global interpreter is locked. So the Python interpreter is being held from being able to handle other requests. And if you're not familiar with the GIL, in simple words, it's a lock that allows only one thread to hold control of the Python interpreter. And this means that only one thread can be in a state of execution at any given point. So if a thread is trying to execute this function is going to hold a lock on it while other threads are unable to execute until that lock has been released. And for this presentation's purposes, we're going to be using sleep to kind of simulate the blocking functionality, though sleep is not a CPU bound task, but just for our purposes, that's why we're going to be using it. So then, yeah, so let's run this function just to kind of give an idea of what I mean. So we're going to run this blocking task. And then we're going to do that same example that we did earlier. We'll make a call to the server. And of course, it's doing some processing. It's waiting the 5 seconds. And during that time, it's unable to take on other requests until you're able to get a response, which then gives us hello world. Now, let's say that doesn't meet our needs right now. We need a way to be able to, still sleep and do a processing in the background, but still allow ourselves to be able to handle multiple requests concurrently. And that's where the first iteration to solving this problem was a form of monkey patching. And monkey patching is a technique by which we are adding or modifying or pretty much kind of like hot swapping behavior for a piece of code at runtime without changing the original source code. So a group of folks at Gvent were the ones I think that got real popular in that implementation, where if we take a look at a coding example for monkey patching, in our example over here, I'm gonna make this bigger so we can see, we have an application that makes a request to google.com. And this is going to be a blocking action for our interpreter. And so when we execute fetch is going to make a request to google.com, and then we're just going to return nothing. We have two functions here. One synchronous function that just does this like 10 times, and then an asynchronous function where we're going to spawn threads to execute this work, and then pretty much execute this function. So let's run that and see what happens. I'll clear this. So in this, when we execute this function, of course, when it comes to the synchronous function, it does exactly what we expect, where it executes the fetch function one at a time in a loop. So we see 1 through 9 for the process ID. Now for the asynchronous function, even though we spawned, 10 different threads, we're still going to see the same type of time, which is 0.6 for synchronous, 0.8 for asynchronous. They're going to still be similar, and you're going to notice that it also executed those threads serially, so one after another, and that's because when the threads try to make this call to google.com, this is a blocking call, and so it holds up that the GIL is being locked at that point until that thread has finished execution, and then the next thread then comes in and does the same thing, applies a lock, and then releases a lock, and so on and so forth. So to get around that, you can hot swap the functionality of requests by doing monkey patching. And so you would use the gvent function, gvent.monkey.patch socket. And what this does, it replaces the underlying socket.getHostName so that it doesn't block the whole interpreter, and then allows the threads to proceed with their requests unhindered. So what this does is each of those threads will be able to run concurrently instead of waiting for each other for that lock to be released. And so when we now run this example, you can see that the original function, let me make this a little bigger, still runs serially one after another with 0.84 seconds, but the now asynchronous function, now that we've attached this monkey.patch, we haven't changed any of the other code yet. The asynchronous function is still spawning 10 threads and then executing that function, but it's doing so concurrently. So all of these threads are not executing at the same time, and then you get a asynchronous time of 0.3 seconds. So there's a huge improvement to your work process, because now, one thing I should kind of point out is that this is only beneficial if the work you're doing is stateless. So if each of those threads don't depend on the results of the other threads, then you're able to have them all execute concurrently and then return the result and go on about their day, because they're not waiting for the result of other threads. So you only really get these performance improvements if your logic that you're working on at the time is stateless, so to speak. So any questions? Actually, before I take any questions, I do want to point out that monkey patching kind of solved a problem at the time, but it does provide other problems. So for example, if you do G event monkey patch all, which I've seen in a lot of places, this is kind of like a spray and pray. It attempts to patch all of the functions that G event have pre-coded in their library and tries to replace them within your application. And what can typically happen is if you patch everything, then when it comes to debugging, now your application is not functioning the way you had initially thought it was, and then you'll run into scenarios where some functions are running concurrently and some others aren't, and now you get into a muddled place of trying to debug, well, what exactly is happening?
Hey, Emmanuel.
Yeah.
I just wanted to let you know too. I actually do stuff that's like very similar to this in my own project. But
okay.
You're using PyCharm, correct?
Yes.
So when you're actually in the debugger, there's a setting that you can actually check to allow the G event stuff to happen, and you'll still be able to get the debugger stuff.
Correct.
Kind of step through synchronously. Just wanted to throw that out there.
Yeah. That's a good point to point out that PyCharm, because of that scenario, have implemented ways to help you debug these type of weird scenarios. But before that, it was kind of tough, and you had to add loggers all over your code just to make sure you know what's going on what thread and why and so on and so forth. But I appreciate that you pointing that out, Dylan. So that's monkey patching in a nutshell. Before we move on to more asynchronous stuff, does anybody else have any other questions?
Yeah, I guess I just had a comment on your Flask example. Like Flask is multi-threaded, so the time won't actually block other requests from occurring because
right.
like the global interpreter lock's not actually going to block on a time that's sleep. It's going to let other things operate at the same time.
Yeah, you're 100% correct. Time does sleep is not a CPU bound task, and so it's not going to necessarily block requests, but I just mentioned earlier that for this purpose of this talk, that's how I wanted people to perceive it, just to because I didn't have enough time to come up with a way to actually block the interpreter. So I was just using sleep as a simple example.
Related question to that. Let's suppose instead of time not sleep, you were doing a task that was truly CPU bound, like
correct,
a real serious like busy loop in the CPU. Would that actually block the entire Flask application from answering other socket requests, other HTTP requests off the socket?
So it depends on the function. So if the threads that are now being spawned to be able to handle the new requests need to use that same function that's being CPU bound, there's going to be a lock on it. They're going to need to wait for that thread to finish execution before they can now pick up execution. So over time, you're going to build up a delay, and then maybe you have a health check that comes to check every 10 seconds. You might miss one of those health checks, which might bring down an application. So just something to keep in mind.
Okay, I was curious if it was basically the same problem with JavaScript. If you block the main loop, you're basically stuck.
Right.
There are cases where you can completely block operation where it's like, because the way that Python decides how to execute code is like because it's deciding between threads like which instruction sets to execute. But if something is truly CPU bound on like one instruction set, then it can block other things from executing. So say you're like trying to parse a gigabyte of JSON or something like that,
right,
that is like one instruction set or something, then you can block completely other threads from executing.
Cool.
All right. Any other questions before we move on? All right. So then the next graduation to solutions for trying to solve this type of problem was the event loop. And if you guys have already done, Node.js development, the functionality is pretty much similar, where you're going to have a single threaded loop that's going to be processing requests as they come in. And then as those requests come in, it's going to register these individual tasks, which we're going to call callbacks, to a queue of work. And those are going to run in the background as the event loop is registering more and more callbacks. And when those operations complete, they're going to alert the event loop which is going to pick up the result and then return that response back to the request. So if we dive into some more definitions, the event loop runs asynchronous coroutines, tasks, and callbacks to perform network I/O operations and run sub-processes. So Python now has introduced the concept of a coroutine, which is very similar to a thread, but differ in how they execute. So in the case of a thread where the operating system, manages the execution according to the scheduler, for the coroutine, it'll be the developer, you yourself, that's kind of managing when to suspend operation and when to resume operation using set points with the syntax async await. This gives you more control over how your tasks are being executed. Another difference is that typically each thread needs to have its own stack with memory allocated for eventual garbage collection. You can sometimes run into a scenario where you have like zombie threads lingering about, eating up memory that needs to be cleaned up. But with coroutines, the execution shares the same stack, and it's kind of kept small because you're continuously unwinding the stack as you're as you're suspending and resuming execution for these callables. So then the ASGI protocol was kind of created to kind of incorporate that event loop. It's a spiritual successor to WSGI and intended to provide a standard interface for async capable Python web servers. So when you define an ASCII server, as I mentioned earlier, it's a specification. So these specifications have been built upon by other frameworks like UVcorn and Fast API and things like that. But with an ASCII server, the protocol pretty much states that you need to have a scope, which is kind of like a dictionary containing details about the incoming connection, the request, and then you would have two callables. You would have one for sending that lets the application send events to the client, and then one that allows the application to receive events from the client. Now, this was kind of beneficial because it allowed you to be able to handle WebSockets in a more in a efficient manner. Because the WSGI protocol, it wasn't really built to handle the WebSocket scenario, and so what they usually did was they would come up with like short polling or long polling to kind of get around the scenario of, let's say, well, let me start from the beginning. Let's say the server needs to be the one to initiate communication with the client. There's no way for a server to do that. This client is the one communicating with the server and then waiting on the server for a response in the traditional sense. And let's say you needed to get information from a server, but didn't know when the server was ready to provide you information. You would poll the server every 5 seconds or every 10 seconds to say, hey, do you have something for me? Do you have something for me? And eventually, if it did, then you would get something. But with a WebSocket, by establishing a channel between the two, the server is free to now initiate communication because the channel has already been created. I like to think of this example as kind of like when you go to a restaurant and you, the patron, you're the client, and the waiter is your way to facilitate a request to the back end, which is like the kitchen, and that would be the server. When you typically go into a restaurant, you don't just show up and food is already there. Granted, that would be great, but usually you would be the patron sending a request and then getting a response. But now with WebSockets, now you technically could, because everyone's machine learning is really popular these days. So let's say it's your favorite restaurant. You could just show up and food is already on the table. The server has already generated a response for you because it already knows what you want. So now more scenarios kind of come into play where you can take advantage of WebSockets. And so then let's see. Oh yeah, and another simple example is the server can keep track of each client. So for example, in a chat app like WhatsApp, you create a group of you and all your friends. You would then send a message to the server, and the server would spawn that message to all of your friends because the connection has already been created. So then let's dive into a very simple ASGI demo of what that would look like. We're going to use UVcorn for that. So, just pip install UVcorn. That helps establish the event loop. And then to follow the example we saw earlier, make this bigger, we have the scope, and then we have a callable to receive information. We have a callable to send information. And I am going to execute this. and run this on the terminal so that when we do HTTP 9000, make a call over there, you can see that it returns hello world. But I do want to point out something very different between the two. So these were our previous calls to the regular Flask server. But the one difference between the two is that now the transfer encoding is chunked. What that means is that you're establishing a way to be able to stream information. In the back, you're sending two calls to the client. The first call is going to say, hey, the request that you provided me, I'm going to give you a 200 saying that the request was a good request, and now I'm going to begin emitting information to you. And so in the first call, we're establishing the connection, and in the second call, we're actually sending the response body. And that's why you'll notice that the transfer encoding is chunked, because we're streaming those into individual mini calls. Any questions on that? So then, if I'm still following along with my notes, let's dive into streaming chunked events. So let's end that server. And in this new example, we're going to take advantage of the receive callable. So everything stays the same when it comes to establishing the response and then sending the response body with the two send calls. But now we're going to actually take in information from a client that's going to be streaming information to us. And you'll notice that we're now using async as a keyword to define that this is a coroutine, and that we're also going to await on the receive body function. And I'll get into what those mean in a second. But for our purposes right now, I just want you to know that the read body function will pretty much sit in a while loop and wait for the client to tell us that it's finished sending us information. So it's going to say, hey, in the message that you're sending me, is the more body key true? That means there's more to send. So it's going to keep on checking, is more body true, is more body true, until it's false. It's going to end that streaming information to this server, and then it's going to return the body back to the client. So let's see what that looks like. So we have, let me run this event loop server. That's just going to be running on 900. And then we're going to stream to our server two messages. We're going to yield hi, and we're going to yield there. And we're going to add a little time sleep between the two, just so that we can see how that works. So we're going to post this information to our client. Let's run that. We're going to send the first message sleeping. This is receive the message hi. And then it's going to send the second message, and then it's received this message there. And then it's going to return back the full body of the message hi there to our client. So just showing you how you're now able to handle these type of streaming scenarios in a pretty seamless fashion using ASGI servers to handle that scenario, if that's a scenario that you want to code for. So any questions on this that we just talked about right now?
So what's the library that's providing the ASGI server here? Is that UVcorn, which basically would stand in place of Flask?
Yeah, that would be UVcorn taking the place of Flask, yes.
Gotcha. So we would run the server, and then you would have a process there waiting to interact with.
Yes. So you would execute it pretty much doing a UVcorn run and giving it the app name, and the same way you would do like a flask.run, and then it would initiate an event loop in the background, and then using async await syntax provided by Python, handle how you're registering callbacks to the event loop.
Cool.
So does UVcorn have the ability to like send, HTML files? Because it doesn't, like, are there like the same concept of routes?
With UVcorn? Yeah. There is a concept of routes. Let me see if I have an example of that. We'll get into that in ACE.
Yeah, so UVcorn, it just implements the ASGI standard. There are multiple servers that are like UVcorn. Mm-hmm. So what I imagine he's going to get into is like using something like Fast API, which is more like Flask, and you still use UVcorn to serve the Fast API server.
Yeah, 100.
It's more like Workbug.
Yeah, correct.
Cool. All right. Any other questions?
The dictionaries you were sending into like that send call, are the structure of those something you just made up, or are they dictated by the API for send and receive?
Oh, these are here. Yeah, these are dictated by the framework that you're using.
Like in this case, these are dictated by UVcorn. Like you have to send type, you have to send status,
Correct.
No,
okay.
I think that's dictated by the ASGI standard. I'm sorry to interrupt, but
Yeah.
I think that's the ASGI standard, because this code should still work on the other ASGI implementations as well, I believe.
That is correct, because these frameworks are still going to implement the specification, but I would imagine there's differences between how the frameworks implement them 100%. But for the most part, I mean, you need a type and you need a status and headers. Those are just kind of like the basics. Imagine there's other things you probably pass in here that might be different between different frameworks, but yeah.
Right. I mean, this is all very HTTP specific. So it's like, if you, in theory, this would be usable for sending any bytes across any socket, but this seems like very focused on HTTP.
Yeah. Cool. So then let's see, we'll dive into async IO. And so this was launched in March 2014 for Python 3.4. So not really that long ago. And I guess the main reason the Python organization kind of needed a way to kind of put their stake in the ground and say, if we're going to be doing Python asynchronously, this is how we're going to do so, was because there were a lot of contenders out there. I think like Twisted was really popular for a while. And there were other frameworks out there kind of doing async Python in their own way. But I guess to kind of add some conformity to the madness, they figured if we're going to do it, this is how we're going to do it, using an opinionated async await syntax. Their idea is that this paradigm achieves high concurrency using a single thread or event loop to manage asynchronous tasks. And it's very similar to how Node.js works. So the idea of an async keyword is it turns a Python function into a coroutine. And a coroutine is something that can now be registered as a callable and run in the background. So there are three types of objects that we can await. And so a coroutine is something we can use the keyword await to. And then you can also await tasks, which are allow scheduling coroutines concurrently. And then of course you have futures, which are promise-like objects, if you're familiar with JavaScript, where it's a placeholder for a value that will be materialized in the future. So let's dive right into code to kind of like enforce those definitions. So in this example, you don't have to pip install async IO, it just comes with Python, you can just import it. And we are going to, let's see, what are we gonna do over here? I think I messed this demo up. Let's see. Okay, yeah. In this example, we're going to pause the execution for each coroutine, allowing the event loop to handle other requests during this pause. And in this function, we're just going to say, hey, after 2 seconds, say hello. And then after 2 seconds, say world. And then we're just going to time it and go on about our day. So let me run this. And it does exactly what we think it's going to do, where after 2 seconds it said hello, then after 2 seconds it said world, and it finished after 4 seconds. So what happens during this execution of work is that we're actually suspending the execution of that task and saying, hey, we're going to wait here for you to finish your work in the background while we continue handling other requests. And then once you're done, we're going to continue execution and then wait again on this next function. But let's say that's not something that we wanted to do. Let's say we don't really care about waiting for each of these functions, and we just want them to be running concurrently so that we can speed up the execution of this workflow. Then you can now wrap the async def function in a task. And so in this next example, we have the same asynchronous function with async def say after, and it does the exact same thing where it sleeps and then prints out the message. But we're now going to wrap them in an async IO.create task. And then we're saying, hey, task 1, you're going to say hello after 2 seconds. Task 2, you're going to say world after 2 seconds. And you're going to both be executing concurrently. So now when we run this example, you're going to see that it only takes 2 seconds for them to run because they both ran concurrently instead of one after another. But I do want to keep in mind that there's a few gotchas with this. If I comment out this await task, what do you think is going to happen? Anybody want to guess?
It's going to wait for a timeout, right?
Oh, yeah, that's a good guess. Let's see.
The whole thing will be blocked.
Let's see what happens. We're going to run this. We're only going to wait task 1, and nothing changes. The reason nothing changes is that it's very important to keep in mind that when you wrap a coroutine in a task, you're saying, hey, I am already registering you as to the queue of tasks that run in the background. So when you hit await and you're releasing the hold on the event loop, those tasks in the background are going to run regardless because they've already been queued up. So even though we only awaited task 1, task 2 is still going to execute in the background because it's been pre-registered already.
So these tasks will start executing immediately as soon as you call create task, right? That initiates their execution.
No.
And the wait is only getting the results.
Awaiting is what releases control of the event loop to allow these tasks to now execute.
So they don't start running until you hit await?
They'll start anytime something else has given up execution. Because these aren't like threads. These are just interleaving executions together. So like the only time it's going to execute is when nothing else is executing and it takes a turn at executing things inside of the coroutine.
Yep.
So are you swapping out so you only swap in or out whenever there's an await keyword, right?
Correct.
Like create task is not swapping to another coroutine and running it for a little bit or anything.
No, you're only
item on a queue.
Yeah, you're only swapping the hold on the execution when you hit await.
So that means that this second task was added to the queue, but then we never why did it run? I guess is the question. If there was never a cycle to come back around and run it.
Because over here, this is where we're registering it to the queue of coroutines to be executed. So if you remember back in that diagram I showed earlier, this is what we're doing when we create a task. We're registering that callback to our queue of work that needs to be run. But this queue doesn't begin running until we hit a keyword await, which releases the hold of the event loop and says, okay, now all the things we have in queue can begin execution. Until they now signal back to us, hey, we're ready, and then takes hold on the event loop again, and then continues execution of that stream of work. If that makes any sense.
Yeah, if you look at when you get to the await statement, it's like saying, hey, I want to wait until this task is done. And then in the task itself, it's going to execute other things that are available on the event loop. And that, in this case, it's those 2 tasks.
Yep.
And I don't think it's necessarily, I'm not sure, but I'm not sure if it behaves like a queue. I'm not sure it's deterministic which of those 2 tasks will always start first.
Right.
And then there's sleep statements in there. And so once one of those tasks hits a sleep statement, then the other one will execute until that sleep statement and so on. I imagine, so if you add the sleep for task 2 to 3 seconds, then there probably will be an error and you won't get the print statement.
Well, that's where things get more interesting because they'll do it after the fact. So let's say we now decide to sleep for 3 seconds on task number 2, the one that runs in the background that we don't care about. When we execute this function, you're going to see hello. Yes. You're going to see hello for the first one because the first is the task that we care about because we're waiting on that specific task to suspend execution. And then we're going to resume execution when that task is complete and prints out finished. And so now that's going to finish. But task 2, let's say you have a long running event loop that's just running forever. It's still going to finish, but it's going to finish in the background after 3 seconds. So now let's change the time to 1 second just to kind of cement that point. You can see that world is still executing in the background and still printing but the only ones we actually care about is the one we waited on, because we're suspending execution right here, and then we're going to print out the finished and move on with our day. But task 2 still technically completes. Cool. So I guess a good example where this might be useful is if you're doing things like, I don't know, logging to Datadog. And logging to Datadog might not be a critical path functionality of your microservice. So you could always wrap those Datadog metrics in a task that runs in the background, and so that the critical path of your application, which might be get into this app, make a database call, and then return the response, you don't get held up in that Datadog metric emit. That would just run in the background and push the metrics to your server. So any questions on this? All right. So then let's see what's next. Futures. I want to dive into futures. As we saw earlier, coroutines are the definition of async. You define a definition by using the asynchronous keyword on a function. A task allows you to schedule those coroutines concurrently, but a future is a promise-like object that has a value sometime in the future. And I see we only have 15 minutes yet, so I'm trying to rush right through this as much as I can. So futures, they're useful in being able to execute pieces of code that are not, that are going to be blocking the event loop or having a hold on the guild. So the only way to be able to tackle those types of scenarios, because not every library has been updated to be able to take advantage of the event loop. So let's say you're using an older library that you know is going to block. So sometimes a lot of these machine learning libraries that were built for like to Python 2.7 still have a lot of blocking functionality in them. You could then execute them in the background using thread pool executors, where you would run each of your workers in a separate thread within the main process, or in a process pool executor, where you would run each of your workers in their own child process. And just to add some more clarity between when you would use the two, a process pool executor would be for CPU bound tasks, and a thread pool executor would be for IO related tasks. So then a real quick demo of what that looks like would be, you have this function that has a task, and all it's going to do is print sleeping, sleep for 2 seconds, and then say done sleeping. We're going to use a process pool executor with 4 workers, because usually the convention is you match your number of workers to the number of cores you have in your machine, and then you execute that task, and then we're going to just see how the future works. So let me make this a little bigger. Execute this. So it's gonna first print out the status of the future, and then it's gonna execute that future, sleeping, done sleeping, and then end processing. So we know this sleeps for 2 seconds. So if we now decided that we wanted to actually wait to get the status of that future, we'd be waiting 3 seconds, and we ran this function. Then you can see that the status of the future is now true, and it provides us that result complete, but we don't actually need to wait on that future to provide us that task, because we know it's going to give us a result sometime in the future. So just a way of, like, if you run into a scenario where you're using async IO and you have blocking tasks that are holding onto your event loop, you can throw them in the background in the process pool or in a thread pool, and still be able to use the event loop in an effective manner. And then, so I just want to show you an interesting scenario that happens if you, because they can still be locking when you use thread pools. And I just kind of want to show you how that happens. In this scenario, what will happen is, and this might get a little confusing, we have only like a few more minutes left, but let's say you have a thread pool executor with 2 workers, right? What's going to happen is we're going to now throw these 2 functions. One, wait on B, that then it waits on the the future result of a variable B future, which is the returned value of the next thread worker, which executes the function wait on A, which is waiting on the A future result, which was a return value of the first worker. And what we should see over here is that they're going to lock, because by the time the thread gets to this point, those variables haven't finished executing because they're waiting on each other. So when you execute this example, you're going to print out the state of the future, and they're both going to be running, but your function, your application never ends because they're both locked, waiting on each other. And it never ever gets to the point where you can print out a result because they're both waiting on each other. Just to kind of reinforce the fact that with threads, they're going to be sharing those variables. And so that's why you can end up in a scenario like this where your thread pool is locking on each other if you're not careful. Granted, this doesn't happen in the thread pool processor because they're not sharing those variables. So in that same scenario, if I executed this example, but using a process pool executor, it's just going to end because we don't, it's a future. So we're not actually waiting on the result. But if we were waiting on the result and we slept 3 seconds instead of the 2, what we should see is some null exceptions because granted, it was unable to get the result for a variable that does not exist within that stream of work. So just something you guys can play around with later if you're trying to walk through these examples. And just before we go, let's see, I just want to point out the fact that number 1 rule of async IO is do not block the event loop. You can run into bad scenarios of like missing your health checks if your event loop is being held on for too long running individual tasks. You can debug for that type of scenario by setting global environment variables, passing these flags in. I'm unable to go through the example with you just yet because I know we're low on time, but it can show you how long, if your event loop is being held up and for how long. And then you can then work to optimize your code to reduce the amount of time the event loop is being held onto. And then of course, my favorite async IO, well, ASGI framework right now is Fast API. The reason I like that, let me jump into that real quick, is because it's self-documenting. So if you wanted to get a really simple server up and running, kind of like how you would do with Flask, you would set your different routes. Oh, let's see. My port is still in use. All right, let's do that. You create your different paths, and then you can go to docs, and you can have this self-documenting API as you build the framework. It all comes. So Fast API uses the unicorn event loop in the background, and then what else? What else with this? No, I just thought that was cool. I threw it out there. So yeah, any questions so far? I'm not gonna throw a lot of at you in the last like 5 minutes, but
that's super cool. I'm curious, like the whole thread pool executor, process pool executor thing, that was sort of predated the async IO, I think, right? How do you use async and await like with that, or do you just not do that?
You do that with those thread pool executors. You wouldn't be awaiting them because they would be running in the background, and you would use this in a scenario.
Okay, so that means you like basically can't await them, right?
No, because they're not coroutines. It would only.
There's a run and executor function, async IO run and executor, where you can await them.
Okay.
Because they're still just futures.
Yeah.
So they can behave like a coroutine, the same.
Okay, but usually the scenario you would use this would be if you have a block of code that is blocking your event loop and isn't being able to run in a registered callback. So things that are like CPU bound, you can run them in the background if they're not IO bound. Because really the main benefit of using async IO, the usual scenario would be if you have an application that has high IO related tasks. So like in microservices, if you're a middleman microservice that one request comes in and then you make multiple requests to other services, gets responses, and then returns a response back to that original request, that's where the event loop becomes really useful because you can throw those IO bound requests into a callable, into a coroutine, and that would execute in the background while releasing the hold on the event loop and handle more requests. So you can have all those different requests happening concurrently. So yeah, Any other questions?
So yeah, just to piggyback off of that, does that mean that the threading in multi-process libraries are kind of replaced by async IO?
So you would say that the multi-threading concept that we used to do before with Python has been enhanced with async IO, with, you know, granted, arguably better syntax, because you wouldn't be making, you could think of, how can I explain this? Because I did multi-threading a little bit, but you could say the select function that you would use in multi-threading to be able to get the result of a thread in like a while loop as you're waiting. If, let's say you have 500 threads and you're waiting on a response, and we call that select function in that while loop, waiting on a response for those threads. That's kind of abstracted away with the event loop. Those callables will now signal to the event loop and say, hey, we're ready to provide you a response and resume execution from your await statement.
I think it's a bit of a different use case as well. So with multiprocessing, you usually have all of your workload, you know, kind of beforehand, so you know how much you need to process. With async, you don't have it all.
Mm-hmm.
So you can process something that is coming in.
That's a good point. Okay.
Can we go back to this future thread pool deadlock.py? This is really cool. I did not know this. Like, so I was super surprised when I saw this, that like the variable b future is valid in the wait on b function. Mm-hmm. So I guess like with threads, I realized threads share virtual memory space, but I didn't know that using them like gets rid of lexical scoping, I guess, which I guess is another difference between threading and the async IO. It's like with async IO, you still get normal Python. Like this is like really interesting.
Yeah, that's why I wanted to throw this example out there real quick, just to kind of show you some of the benefits of scenarios you wouldn't typically run into on the event loop and using coroutines.
In this example, the reason why that happens, if I understand properly, and please correct me if I'm wrong, the A future and B future variables are defined at the module scope, but they're global to the module anyway. And that's the reason why wait on B and wait on A actually have access to those variables, because they will be defined by the time those functions actually execute. The fact that they create a deadlock is because of the fact that they both exist on the same, like the two threads share them, right?
Yes.
And now they're going to be waiting on each other.
Yeah, they're waiting on each other to finish, but they'll never finish because they're unable to continue execution.
So it's still lexical scoping, but it's like because
how are they defined at the module scope? Is that just something special about the main function?
Well, it's not a function. That if main equals
main, you're right. Oh yeah.
It looks like it looks like it'd be introducing a new scope.
Okay, yeah. Everything makes sense again. I was like super.
That caught me too.
Cool. So I tried to condense as much as I could in 1 hour, but as this conversation has already shown, there's a lot to this stuff. Maybe we could be here for another 2 hours. So on that note, quick plug, it's plug time. I am thinking about trying to build like a course around this stuff. So here's my social links, but if you are interested in when I finish getting this course together, you can leave your email on this link, because I would actually like to give the course for free to a few people, just so that y'all could probably review it and let me know if I'm talking out my ass or something. But yeah, just let me know if you're interested.
It's super helpful.
Awesome.
Thank you, man.
For sure.
Yeah, thanks so much, Emmanuel.
Yeah, thank you.
These examples were awesome.
Great. Well, then I'll send out a follow-up email. We'll have the recording up in a few days here, so I'll send that out too, in case it's just a helpful resource to like go back and look over anything we talked through. But yeah, thanks everybody for joining, and we'll be in touch.
Yeah, appreciate you guys coming out.
Thank you.
Awesome. Have a good one.
Thank you very much. Yeah, thank you.
Bye.